Energy availability and its use is fundamental for several applications and services in human societies. Nonetheless, the modern energy system may be harmful for the environment and contribute to serious troubles in society and economy. There are tangible effects on the physical world that are straightforward. This can be related with the different steps of the energy transformation process from primary resources to final consumption and include both the exploitation of natural assets and the accumulation of natural liabilities. Natural assets account all natural resources that technology can turn into valuable goods for humankind. All energy stocks and flows we have surveyed so far are an example of natural assets. On the other side, natural liabilities include the accumulation of harmful substances in the natural world. For example, the accumulation of greenhouse gases in the atmosphere is an example of natural liability. Tangible effects on the physical world easily evoke pictures of natural disasters directly or indirectly linked with energy utilization. The Bof Cemetery of Muinak in the Aral Sea proves the irreversible decline of a natural ecosystem originated from the diversion of natural resources. Similarly, a street from Pripyat is an inflexible reminder of the ecological, social and economic collapse originated from the shallow utilization of technology. Pripyat was abandoned the day after the Chernobyl's explosion in April 1986 and almost 30 years after is a symbol of the Chernobyl's legacy for humankind. However, there is a basic concept that is worth mentioning again. When energy flows from one body to another, both of them change their condition, while the environment undertakes permanent modifications. The magnitude of these effects is related to the amount and type of energy flow. This is the essence of the second law of thermodynamics, which says that all physical phenomena are always irreversible. Energy resources and materials that are early harvested are introduced into the world energy system. After a long chain of processes, they feed and use devices that are designed to produce useful effects. Afterwards, they are discharged into the environment in forms that are no more usable. Energy flows that supply end users are less than TPES because of transformation losses linked to technology imperfections and thermodynamic irreversibility. In particular, both useful and lost energy are released into the environment in form of heat and materials at high entropy that are no longer usable. Energy flow estimates are annual average power measured in terawatt that, remember, is the ratio between the amount of energy in terajoule and the duration of the exchange process in seconds. This argument depicts a thermodynamic arrow of time that is a consequence from the second law of thermodynamics. The conclusion is inevitably the same. Each time energy is used, whether in natural or artificial processes, the environment is modified accordingly, with no possibility to restore the original state. Let us now consider some relevant examples of harvesting natural resources from humankind. Overall, it is necessary to recognize that photosynthesis remains the most important energy conversion in the biosphere because it transfers energy to life. Indeed, it is the pillar that supports all heterotrophic life, human life included. It is therefore paramount to understand what humankind can harvest from biosphere. We said that the net primary productivity, NPP, determines the amount of energy that is potentially available for transfer from vegetation to the other levels in the trophic webs of ecosystems. The human appropriation of net primary productivity is estimated at 25%, It includes all crop harvest used directly for food or indirectly for animal feeding. Moreover, it accounts for all harvest of woody phytomass, whether for fuel, construction timber, paper industry, and so on. About 50% of the overall human withdrawal of carbon resources from the biosphere's flow is indeed for crops. Land used for grazing takes about 28%. There are also other contributions from human-induced alteration of forests and fires. Finally, about 4% of NPP is lost due to change in land use to accommodate human infrastructure. The huge increase in world population in the 20th century, with increasing demand for food, raw materials and energy, is seriously endangering global stocks of phytomass. In the last centuries, the global phytomass gradually reduced as population increased. It is worthwhile noting that not only population increased, but also the per capita appetite for energy. Finally, we talk about how humanity collects, flows and energy stocks. The amount of energy that mankind can gather from the biosphere is inherently limited by the energy process that feed our planet. The radiative balance with the Sun, the heat transfer from the deep core of the planet, and the action of gravity of other celestial bodies. Humankind collects energy for its own needs from various sources, with one major difference. The energy supply from renewable flows is far less than the one coming from fossil stocks, being an issue the fact that they will sooner or later run out. There is a further concern. Most of the flows and stocks of energy used by human civilizations are connected to photosynthesis. More than 80% of TPES comes from stocks of fossil photosynthetic products, that is oil, coal and gas. In addition, 25% of NPP is critical to provide food and other services to human beings. There is a manifest threat in the relation of nature and humankind, a Damocles sword that encompasses the dependence of human energy use on photosynthetic process.